Hello and welcome. I'm going to use this video to go through the Math 242 review topics outline and do a few examples that are mentioned in the outline as a way for you to see some of the things that you should go back and review. This won't be comprehensive, but you can use this video and the outline itself to help you decide what you should focus your studying on, where to look for examples, and to remind you of topics that you may not have thought about in a little while. I'll start by running through what I think are some of the important topics, just selected topics from the outline. We'll start with Unit 1. A lot of this is stuff that we've been using all along and might seem kind of easy now, but I want to remind you of some of the kinds of problems that we used to do back at the beginning of the term. I'll start with the problem that's highlighted here from the outline. This was similar to a quiz question that we had earlier. I'll start by drawing my 3D axes in the usual way, and then let's try and draw this line where z equals 2 and x equals 5. So I'll mark z equals 2, x equals 5, and let's try and draw that line. I didn't specify what y was. This point that I've drawn here looks like it's where y equals 0, but I didn't specify y, so this would be a line parallel to the y-axis. And we're supposed to draw a cylinder of radius 3 centered around that line. So I'll do my best with this. It doesn't have to be perfect, but it has to be a radius 3 cylinder centered around that line. And so the questions here are easier to answer the more careful I am about what my cylinder actually looks like, although I didn't do a great job of actually centering it on the line. I wanted to make it look like it had radius 3. So the first question was, does it touch the xy plane? You can see I tried to draw it so that it sort of does seem to dip below the xy plane, and the reason that I knew it would is that I know this line is 2 units above the xy plane. I knew that because it's centered along the line where z equals 2 and x equals 5. And since the radius is bigger than that, the radius is 3 of the cylinder, that means it must dip below the xy plane. The other question was, does it touch the x-axis? Well, if it seems to be going below the xy plane, then it seems like right around here it would be touching, and here it would be touching the x-axis. So in both cases, it seems like the answer is yes. However, it doesn't seem like it would touch the z-axis because the center of the line is 5 units away from the z-axis, but the radius is only 3. So it does touch the x-axis, does touch the xy plane, but it doesn't touch the x-axis. So hopefully problems like this sound at least a little bit familiar to you. You can go back look at the worksheet, go back and look at the videos for more examples like this. And that's generally what I'll encourage you to do for a lot of the topics. Let's go on to some of the other topics from Unit 1. Most of this stuff from the very first day is stuff that we've been using all along, and so we might not need to review it so much. But I think dot product and cross product are things that we might not have thought about quite so much recently. So let's take a second to remind ourselves, first of all, of the properties of dot product. So dot product has a simple algebraic formula. If we take the dot product of the vectors a, b, c, dotted with the vector d, e, f, we know the dot product gives us a scalar, a times d plus b times e plus c times f. So think of that as the algebraic definition of the dot product. But what you might also remember is that geometric definition, which is that v dot w is equal to the magnitude of v times the magnitude of w times cosine of theta, where theta is the angle between v and w. Let's say a little bit more here, because if you wanted to find that angle theta and you knew what the vectors v and w were, you could solve for theta in this equation by dividing by the magnitudes of v and w and then taking arc cosine of both sides. The most important application of this idea is that since cosine of pi over 2 is 0, we can tell when vectors are at an angle of pi over 2, that is when they're perpendicular or orthogonal. If v dot w is equal to 0, then that theta must be pi over 2. So we say that two vectors are orthogonal or perpendicular whenever their dot product is equal to 0. Another topic we haven't thought about in a little while is vector projection, which is related to dot product. So if I have two vectors, v and w, what then is the vector that's the projection of v onto w? The way we write that is the projection of v onto w. So I always think of like the proj is standing on top of the w. So we sort of think that we're projecting onto w, so take the shadow of v onto w. And so here's the vector that we're talking about. I've formed this little right triangle. And remember that the projection onto w ought to be parallel to w. Is sort of a way to remember which way that you should be projecting. As another example, let's consider a case where v and w make an obtuse angle. So first of all, using our dot product formula, we know that v dot w should be positive when they form an acute angle and negative when they form an obtuse angle. If we're trying to draw the projection here, it's not super clear how to do the projection of of v onto w. But I can still try and form this right triangle. I just have to kind of extend the vector w backwards. If I'm thinking of the vector w sort of as the floor and I'm finding the shadow on the floor, I just have to form my cross product back here, and so the projection vector is this one. Again, it's still parallel to w, it just happens to have the opposite direction. There's a formula for vector projection that I'll have you go back and look up, but I think the geometry is the part that is sort of the easiest to get confused. The next topic is cross product, and again, let me just remind you of some of the important properties of cross product. So first of all, there's kind of a complicated formula for cross product. So I'll just say, first of all, you have to know the formula. And by this, I mean the algebraic formula. And I'm not going to write that down right now, because what I really want to know is the geometric characterization. So the next thing to know is that most important thing is that v cross w is orthogonal, so that is perpendicular to v and perpendicular to w. So this tells you what the direction of the cross product is going to be. It doesn't quite, because there's two directions that are going to be perpendicular to both v and w, but you can use right-hand rule to decide which of the two, and I'll have you look up what that means if you don't remember. The second important thing to know about cross product is how to find its magnitude. I've described what its direction does, but how about the magnitude of the cross product? Cross product is a vector after all, so we can ask what its magnitude is. The formula is similar to the formula for dot product, except this one involves sine of theta instead. And still, theta is the angle between v and w. So a consequence of this is that if we wanted to know when the cross product is 0, that would be when sine of theta is 0. That occurs when theta is 0, so when v and w have the same direction, the cross product is going to be 0, or when theta is 180 degrees, or pi radians. And so that would be when v and w have opposite directions. So it's different than cross product, or sorry, different. Cross product and dot product are different in that dot product is 0 and the angles are, the vectors are orthogonal, and cross product is 0 when the vectors have either exactly the same or the exactly opposite directions. The next part I want to talk about is lines and planes, because these are, I think, a kind of a tricky topic to work with, and you haven't had much practice with lines and planes recently. So let's first talk about lines, so how to parameterize a line. So remember, to parameterize a line, you need to have a point on the line and you need a direction vector. So if you know a point on the line, and let's just call that point P, and you know a direction vector V, then we can write down the parameterization for the line as R of t is equal to, well, you take your starting point and then you add any scalar multiple of the direction vector to it, and you'll get another point on the line. So remember what the idea is when we try and parameterize lines or curves. Every value of t gives you a different point along the line. And so when t is 0, we get our starting point P. When t is any other number, we get a different point along the line P, along the line. Now let's talk about writing down the equation for a plane. So at this point, we're not going to try and parameterize the plane. We're going to write down an equation for the plane. So remember that to write down the equation for a plane, we need a point on the plane and I'll just call it XYZ. Or sorry, I'm going to stick with the old notation here. Let me call it instead, we'll call it ABC. And we need a normal vector. So remember that a normal vector, normal means perpendicular to the plane. So to draw a quick picture here, before I actually write this down, how to do it, if we have a plane in 3 dimensions, so this is supposed to be a 2D plane living in 3 dimensions, we know the point ABC is on the plane. We'll know a vector V that's supposed to be perpendicular to the plane. And if I have any other point that is on the plane, then there are 2 vectors that are orthogonal to each other. V is orthogonal to this vector from ABC to XYZ. So I can write that down as an equation. We know about dot product. We can tell when vectors are orthogonal. V being orthogonal to this displacement vector, x minus a, y minus b, z minus c. Well, if they're orthogonal, that ought to be 0. So if you knew the vector v, you could multiply this out. Now, after learning about lines and planes and how to describe them, you might remember we had lots of different problems regarding lines and planes, finding the angles between them, distances between lines, planes, points, finding the closest point along a line or a plane to a different one. There's all kinds of different problems we could ask about here. And so I'm going to just do one example, and just so you can kind of remind you of the flavor of these and the kinds of tools you'll need to use. So here's the typical example of the kind of problem we might ask. Find the distance from a certain plane to the point 135. I like to always start by drawing a picture here. And I'm not going to try and draw exactly the correct plane or exactly the correct point. I'm just going to draw a plane and a point so that we can get a general picture of what's going on and what kind of problem we're dealing with here. So here's my plane and here's my point. And I'll encourage you to pause the video for a second and think about a strategy for finding the distance from the plane to the point. Now, when I say finding the distance from the plane to the point, I'm sort of imagining that you're going to think about the closest point on the plane to the point. That's always what I'm going to mean by distance from one object in 3 dimensions to another. It's sort of the closest distance you could have. And I'm imagining that, the closest distance would be the one that's connected by a line, and not just any line, the line that's perpendicular to the plane. So I've sort of turned the problem that I started with into a different problem. If I can find the line that passes through my point 135, and is perpendicular to the plane, then I can try and find that intersection point, the red point, and then measure the distance from the red point to 135. So I sort of have a multi-step strategy. So I'll say find the blue line, which goes through 135 and is perpendicular to the plane. Find the red intersection point. And then find the distance. Okay. There are other ways of doing this problem. Some of them are a little bit more sophisticated maybe than this one, but this is the one that sort of occurred to me first. And so I'll go ahead and just sort of show you what tools are involved in doing something like this so you can see the kind of problem-solving strategy that's helpful for problems like this. So let's try and go through this one at a time. We'll find the blue line that passes through the point 135 and is perpendicular to the plane. Well, what do I need in order to find the line? Well, I should write down the parameterization. So I need I need a point on the line, and I'm going to need a direction vector. So I need a point on the line, and we have one, right? We have the point 135, and we need a direction vector. And the direction vector for this blue line could be the same, and it should be the same, as the normal vector to the plane. So the normal vector to the plane, you can remember that we can just read this off as the coefficients of our equation for the plane. So the normal vector to the plane, the normal vector to the plane is 1, 2, 3, and that also serves as the direction vector. And so to write down the parameterization for the line, I can say that it's r of t equals 1, 3, 5 plus t times the vector 1, 2, 3. And so that simplifies to 1 plus t, 3 plus 2t, and 5 plus 3t. Okay, the next step was to find the red intersection point. And I'll scroll down to make some more room for myself. So here I need a point that's both on the plane and that's on the line. So remember what the line is telling me. It's telling me that x equals 1 plus t, that y equals 3 plus 2t, and that z is equal to 5 plus 3t. So I can actually just take the equation for the plane that we started with and make those substitutions. So it's x plus 2 times y plus 3 times z. And that all ought to be equal to 4. Okay, so I'm not going to finish this problem because I want to go on to other things, but I'm going to sort of talk through what you would need to do to finish the problem out. First of all, you'd need to solve for t, and then plug that t back into the parameterization for the line. So we'll solve for t, and then plug in to the parameterization up here. Then we'd know the coordinates of the red point. And once we know the coordinates for the red point, we can go about doing our last step, which was just to find the distance from the red point to the point 135. Again, every problem is different. All of these lines and planes kinds of problems take different forms. You've seen a bunch of them, so I'll encourage you to go back to that day in your notes, those videos, to see more examples, to see the kind of variety of problems we can ask and what kinds of tools we use here. Often you use dot product or cross product. You need to know a lot about points and lines and planes especially. And there's different kinds of problem solving and strategizing that are involved in the different kinds of problems. Returning to our outline, the next unit was on curves in 2 and 3 dimensions. The one topic that I think is maybe the best to review right now is to remind you about curvature, because we're supposed to think about curvature as the rate of change of the unit tangent vector with respect to arc length. So let me say a little bit about that. Let's say I have a curve like this that's bending sort of quickly compared to a curve that's not bending very quickly. So if we take 1 unit of length along the curve, let's say this is 1 unit of length along each of the 2 curves. So these are supposed to be the same length. The question is, how much does the unit tangent vector change from one point to the next? So here's a unit tangent vector, and here's the one at the other end. I'll do the same thing here, but you can see that the unit tangent vector is not going to change very much from one point to the next. Right? As I go 1 unit along the curve, if the curve is bending tightly, then the sense of direction, the unit tangent vector, is going to change a lot. If the curve is not bending tightly, then the unit tangent vector won't change very much. And so that's where the formula for curvature comes from. That the curvature, we usually use a lowercase kappa for curvature, is how fast t is changing along the curve. To be more precise, it's the rate of change of t with respect to arc length. And I want curvature to be a scalar, so I'm going to make it just the magnitude of that. Now, this is often difficult to calculate directly, so you can use chain rule, and this ends up being, well, the magnitude of, and if we use chain rule correctly, we can say that it's dt hat dt. If we parameterize the curve, it's not hard to get a formula for t hat in terms of the parameter. And then ds dt, but as we'd seen, ds dt is really just the speed. So the more compact formula is to say it's the rate of change of the unit tangent vector with respect to the parameter divided by this speed function, remembering that speed is the magnitude of arc time, the magnitude of velocity. The rest of this stuff I'll encourage you to just go back and look up if some of this is not looking familiar to you. But I'll go ahead and go on to Unit 3 now, multivariable functions and their differential properties. So one of the trickiest thing about multivariable functions is distinguishing among the different visual representations of them. So I'm going to go through a couple examples of this right now. I'll start with a function that we're pretty familiar with by now, that f of xy equals x squared plus y squared. Now, some people might look at this and right away say, it's a circle. And some people might look at this right away and say, it's a paraboloid. And you're both sort of correct, but you were talking about 2 different representations of the same underlying function. So let me just kind of say these 2 definitions, and then we'll go through how you would actually figure out what they look like. First of all, we know that the contour plot or level sets of the function this is where the function is equal to various constants. So these are sets along which f is constant. So let's try and draw a picture of the level sets for this function. So this is going to involve setting the function equal to various constants. So let's start by saying what happens if we set x squared plus y squared is equal to 1. Well, if x squared plus y squared equals 1, we know what shape that is in the xy plane. Notice that x and y are the only inputs here, and so I'm not trying to draw a 3D picture, I'm just drawing a picture in the input space. So this lives in the input space. Oops. So in this case, just x and y. So here's what I get when I set the function x squared plus y squared equal to 1. It's a shape just in the x's and y's, just in the input space. Let me choose a couple more constants. If I say x squared plus y squared equals 2, okay, that's a circle of radius root 2. So I'll draw that circle. If I wanted to do x squared plus y squared equals 3, that would be a circle of radius root 3. And it would be good to label each of these also. 1, 2, 3, and you can see I'm color coding them. I could also do something like saying, what's x squared plus y squared equals 0 look like? Well, that would only happen when x and y are both 0, and so that must be down here. So this gives me an idea of what the function is doing for different points in the plane, for different inputs. You can see what's happening. The concentric circles have larger numbers associated to them the bigger the circle is. And I can see that this function is larger the further away from the origin that I'm getting. And so that's information about the function. It tells you what the outputs look like for various kinds of inputs. And so the contour plot is a good way of being able to see what the function's doing in different places. The other main way of visualizing the function is using the graph. And this is where we introduce an extra variable as the output. So setting an extra variable as the output. In this case, since x and y's are the inputs, I'll have z as my output. So this is going to be a picture in 3 dimensions, the 2 input dimensions, x and y, and I'll use z for my output. These are ideas that we've talked about for a while now in the class, but I think it's maybe helpful to come back and sort of see them being put together. And the relationship between the two pictures is that the horizontal slices parallel to the xy plane of whatever this graph surface looks like are going to look like the level sets. They're going to look like the contours. So at height 0 when z equals 0, we're just going to have that dot. At height 1, we're going to have that circle, x squared plus y squared equals 1. So I'm lifting that circle up to a height of 1. When z equals 2, we'll have this circle of radius root 2. When z equals 3, we'll have this circle of radius root 3. Now, okay, there's values in between 0, 1, 2, and 3. I can include fractions and irrational numbers and stuff. So if I strung all of these together, we get a better sense of what the graph of the function looks like, and it is this familiar paraboloid shape that I mentioned earlier. Yeah. So what I'd like you to think is that these are two different visual representations of the same underlying function. It's not that one is any better than the other, but they both help us see the function in different ways. The function is something that takes in two inputs, x and y, and gives you an output. So we can either see the output as height, the z value, or we might want to see the output in the input space by just labeling it with a different color or a different number and drawing the contour plot, the level sets. Throughout this semester, we've asked you to look at contour plots and try to draw information from the contour plots about what the function is doing. Here's a contour plot of just sort of a random function that I drew, but I want to see if you can take a look at it and see what information about the function g of xy you could get out of this. Can you see, are there any maxes, local maxes or local mins? Are there any saddle points? Where is the function the greatest and where is it the smallest? And could you imagine what the graph of the function would look like? There are lots of things that we've asked you to do with contour plots, and I'll encourage you to kind of think back throughout the semester about what those were, and also to just get some practice and reacquaint yourself with them if you haven't thought about it in a little while. Some other things from early on in Unit 2 were identifying quadric surfaces, and I'm going to write one down, and I want us to think about, if you couldn't remember exactly what this looks like, would you be able to figure it out? And I think one of the useful tools for figuring out is thinking about the cross sections. And you think about cross sections by setting variables equal to constants and thinking about what they would look like in the plane defined by the other two variables. So for example, if z is a constant, what do we get in the xy plane? If we set z equal to a constant, then x and y are the only actual variables left. And so we'd get something like x squared plus y squared equals a constant. And so we'd get a circle, right? So this tells us that we have circular cross sections where z is a constant. And that sort of tells us that we have rotational symmetry around the z-axis, that all of the cross sections, all of the horizontal slices of this surface would be circles. Okay, what if we try a different variable? What if I set x equal to a constant? And I'll keep things simple here by saying if x equals 0, what does it look like? So now we're just left with the y and z. Well, let's think about what our equation is. It's y squared minus z squared equals 1. That's a hyperbola, right? And we can see that if y were equal to 0, we wouldn't have any points because we'd have negative z squared equals 1, so z wouldn't exist. But if z were 0, then y could be plus or minus 1. And so that sort of tells us which way the hyperbola has to open. It has to be this kind of hyperbola. Now, putting those pieces of information together, we can try and get a rough sketch of the surface in 3 dimensions. We know what its cross sections look like in a couple of different directions, and so we can try and draw what the surface looks like. We know that it has rotational symmetry around the z-axis because all of the cross sections parallel to the xy plane are circles, and we know the profile, the cutout when x equals 0, is this hyperbola shape that opens in the y direction. So on the one hand, we know that the profile in the yz plane looks like a hyperbola, and we also know that the cross sections parallel to the xy plane are these circles. And so this maybe helps us see that this is a hyperboloid of one sheet. And you can look back at some of the formulas in the video, especially in the textbook, outline pretty clearly when you should be expecting to see a hyperboloid versus a paraboloid versus an ellipsoid, etc. But having these tools about being able to distinguish if you forget that sort of thing will also be useful for you. The next thing that I want to talk about is partial derivatives. We're pretty good at calculating these now, but one thing that I think was challenging early on was how to identify and visualize them from either the graph or the contour plot of a given function. So I've drawn a little contour plot here, and I want to see if we can visualize at least whether these partial derivatives are positive, negative, or 0. And I think this will be good practice for deciding, for reading these contour plots as well. So the first question asks us about fx at the point P. And so we're trying to ask, is this function increasing or decreasing as we go in the x direction, as x increases? So as I go in the x direction through the point P, I'm going from 4 to 3 to 2. From 4 to 3 to 2. So that seems like we're decreasing. I'm not asking about whether y is increasing. I'm asking about whether the function, which we can see through the labels here, is increasing or decreasing as we go in the x direction. So that seems to be decreasing. So I'll write that this is less than 0. This partial derivative is less than 0. However, as we go in the y direction, for f sub y, we're going from 2 to 3 to 4. From 2 to 3 to 4 as we go in the positive y direction. So that's increasing. So f sub y of p, partial derivative with respect to y, would be positive. Directional derivatives is a similar idea. If we take this vector negative 1 over root 2, 1 over root 2, well, that's going this way. And so that we can see is also going from 2 to 3 to 4, so that one also must be positive. One of the trickier points, though, is that if I go in a direction, and I'm just going to call this vector u hat, and if I do the directional derivative tangent to the curve, well, I'm going along the contour. I'm going along the level set. And remember that the level set is a curve along which the function is constant. So if the function is constant along this curve, and I'm going in the direction of the curve, then that rate of change ought to be 0. I'll skip ahead a little bit now to linearization. And mostly I want to clarify some questions that came up about the notation that we use here. Linearization, I'll have you look up the formula, but the linearization helps us estimate nearby values of a function based on a known value. So we can estimate the value f of xy if we know f of ab and xy is close to ab. So the formula is something like this: L of xy equals f of ab. Again, thinking of ab as a point that we already know about, plus fx of ab times x minus a plus fy times y minus b. So if you know f of ab, fx of ab, fy of ab, then this is supposed to give you an estimation for f of xy. The linearization estimates f of xy. If xy is close to ab. A different way that this formula was stated is really not all that different. It's just sort of a difference in notation. I'm going to rearrange this equation just slightly by moving the f of ab to the other side. And then rewriting some of these variables, because this L of xy minus f of ab, this part is approximately equal to the change in f. Likewise, I can say that this x minus a, we think of that as the change in the x value from the base point ab, and y minus b is the change in the y value from the base point ab. So this often gets written as delta f is approximately equal to, and just using the different notation for partial derivatives, I can write it this way, and this is often rewritten as something like df equals df dx plus df dy. And the fact that I'm using dx instead of delta x sort of signifies that this equation is really only true for in the limit as dx, delta x and delta y approach 0. You can see that in part E I said make a list of everything you need to know about the gradient, because we talked a lot about gradient here. I'm going to put that on hold for a second and come back to it towards the end, but you can see in the footnote there are a lot of ideas. For optimization, though, let me remind you of a couple of key points. When we say a critical point, I'm talking about a point at which the gradient is the zero vector. That is where fx is 0 and fy, both partial derivatives, are 0. And so that tells you that you have sort of a flat spot, which could be a hilltop or a bottom of a pit. That is to say, something that could be a local max or a local min. You can tell whether it's a local max, local min, or neither using the multivariable second derivative test. And we've talked a lot about the difference between a local max, which is the highest point among those nearby, versus a global or absolute max on a particular domain, which is just the highest value that the function takes on that domain. I wrote down sort of an example here that I'll talk through a little bit. I won't actually do any calculations because I didn't give you a function, but I think it's helpful to sort of think through what you would need to check in a problem like this. And this probably reminds you the most of the extra credit question from quiz 4. So the region being defined here is where y is between 0 and 1 minus x squared, which is sort of an upside down parabola. So I'm talking about this region in here. So here's the region R. And the way that I like to think about these problems asking for a global max or min, the global max or min can happen in 3 ways. It can be on the interior, which would mean that it's a critical point, meaning that we'd need to set the gradient equal to 0. Or it can occur on the boundary. And the boundary here really has 3 pieces. It has the 2 edges, edge number 1, edge number 2, and it also has these 2 vertices. So there's really 4 things to check along the boundary. And then finally, or there just isn't one. So these are the 3 possibilities for a global max. Either it's on the interior, in which case we're looking for critical points. It's on the boundary, in which case it's either on one of the 2 edges or one of the 2 vertices, or there just isn't one. However, this last possibility, we have something that tells us when this may or may not occur. Since this region R is closed and bounded, closed meaning it contains its own boundary, that's the less than or equal to signs rather than just less than signs. Bounded meaning it doesn't extend infinitely far in any direction. But if it is closed and bounded, that means there definitely is a global max and global min. So in this example, this one doesn't work. There has to be a global max and a global min, so we'd need to check the interior, that is look for critical points, and that comes from setting the gradient equal to 0. We could check the boundary, which involves checking the top curve, the bottom curve, and the 2 endpoints. And then the last possibility doesn't happen. So the vertices are sort of easy to check. We just can figure out the coordinates. But the 2 edges, we have 2 methods for doing it. One is that you parameterize those edges, and then you reduce the problem down to just one variable, the parameter t, and you can set that, the derivative of that new function with respect to t equal to 0, looking for critical points of this function to just one variable. The other possibility is using Lagrange multipliers, which was one of the optional videos. Another way you might think about finding the global max and global min is to think one dimension at a time. There's the 2-dimensional interior, there are the 2 1-dimensional edges, and there are the 2 0-dimensional vertices. And so that sort of tells you the different regions that you might need to check when looking for a global max or global min. The next unit was about double and triple integrals. Let me take a second just to say what we mean by an integral very generally, because we've seen a lot of different integrals and different kinds of integrals in this class. First of all, whenever I say an integral, I want you to think of this as a process. So the integral of a function, and I'm sort of thinking about double integrals right now, but the same basic idea is going to apply to all different kinds of integrals on a region. So there's two elements here. There's the function and there's the region. And I want you to think of this as the result of a process. The first step in the process is that we're going to slice the region up into bits. So thinking about a picture, if I have a region R, I'm imagining slicing it up into little bits. We've seen how to do this both into little squares in a rectangular grid. We've also done it in polar, and in 3 dimensions we've had a few different ways of slicing our region up. But then the second step is going to be to approximate on each slice. So the kind of thing that I'm talking about is taking the value of the function on that slice times delta A, where delta A is the area of the slice. Sometimes we write X star and Y star here. Then we're going to add up those results and take a limit. So why would we want to go through such a complicated process? Well, remember some of the early examples, and the kinds of examples that I'm thinking of are the ones that we saw in the worksheets, such as population density. If you knew the population density were constant, so let's say 1,000 people per square mile, you could just multiply the number of people per square mile times the number of square miles. However, if the population density depends on position, that is, if it's a function of position, that doesn't work anymore. What you can do is approximate on each slice by slicing up the region, approximating the population kind of one slice at a time, because the population density is basically constant on each slice. So you can approximate on each slice and then add up all of those slices. So in this third step, you're getting an estimate for the entire population. And then we can sort of intuit that that estimate would get better and better the more slices we take, and that's this last step of a limit. If you look at the formula for the integral of a double integral or triple integral, you'll sort of see all of these pieces in that formula. You'll see the add them all up as some kind of summation sign. You'll see the f of xy times delta a in there. And you'll also see the limit in there. Now, I'm not filling in all the details, but this is sort of an explanation as a process of the formula that you end up with. And I think the population density is a good example to come back to if you're trying to remember what the double integral is supposed to be telling you. There are, of course, a few other applications that you can see I've written in the footnote of the outline. And similarly, there are a bunch of applications of triple integrals that we've seen as well. Also, in this bullet point, I want to kind of remind you of some of the things you have to think about when setting up double and triple integrals. You need to think about how you're deciding what order to write the integrals in, how are you deciding what the limits of integration are, stuff like that. Same thing for triple integrals, and same thing in Unit 5 when we were using different coordinate systems. The best way to review all this is to go back to some examples. It's hard to really give like a general outline here, but if you look back at the examples we've done in section for homework, in the textbook, on the videos, you'll see some good ideas about what kinds of techniques are going to be important. When we come to Unit 5, one more thing I want to say about Unit 4 is that we'd seen that you can use double integrals to calculate certain volumes. But I'm going to say if you see a problem that says calculate the volume of something, a triple integral is a better way to go. remember that triple integrals, you can take the triple integral of 1 dv is equal to volume. And in general, this is an easier way of thinking about volume than trying to do volume with a double integral. That was a useful way to think about double integrals early on, but from now on, I think it makes more sense to calculate volumes using triple integrals. When we get to Unit 5, this was when we started talking about doing double and triple integrals using other coordinate systems. The kinds of things that I'll mention right now that I think are really useful practice. In part C, it says, what are some easy to describe surfaces in each coordinate system? Think about what happens if you set rho equal to a constant. What happens if you set phi equal to a constant, or theta equal to a constant, or r equal to a constant? What do the shapes look like for each of those? What happens if you take 2 out of the 2 out of the 4 of these, and you set them equal to constants? What shapes do you end up with? Thinking about sort of simple equations you could set up with here might be good practice for remembering what these variables represent and then being able to use them when you're setting up triple integrals and finding bounds for them. When you are converting an integral into one of these coordinate systems, I usually say that there are 3 things to think about. I say you have to think about your bounds, you have to convert your function into the new coordinate system, and you also have to convert your differential. When I say the differential, I mean the dA or the dV. I'll also mention that these are the same 3 things that you have to think about when you're using U substitution back in Calc 2 when you were doing integration using U substitution. You can think of doing integrals in different coordinate systems as a multivariable version of U substitution. The next segment of the course was about line and surface integrals, but to start with, we talked a lot about vector fields. So the point that I'm going to focus on here is this third point about what it means for a vector field to be conservative. So remember that a vector field is conservative means has a potential function. So that is to say that the vector field is equal to the gradient of something. So the way I've written it here, I'll say that lowercase f is the potential function for the vector field capital F. In the same way, I could say that capital F is the gradient of lowercase f. And you've done some examples of this already, but I'll just kind of go through 1 or 2 here and just say that if I asked you to find the potential function of, say, the vector field z, y, x, so let's say this was the capital F, and I said find a potential function for that. Well, there's a few ways you could proceed. I mean, the way that I would probably start is I'd say, okay, I need a function f of x, y, z so that the gradient of f is equal to this whole thing. And so that tells me that I need fx to equal z, I need fy to equal y, and I need fz to equal x. And as I go through this, I'm going to say, okay, well, the derivative of f with respect to x should be z. So I might just take a guess here and say, okay, what if f was xz? Now let's see, let's check my guess. Derivative of, what's the gradient of xz? Derivative with respect to x is z, that works. The derivative with respect to y would be 0, which doesn't match. Looks like I need to correct my guess by saying, okay, what if I add a 1/2 y squared to get that second part to work? Let's check again. Derivative of f with respect to x is z, that works. Derivative of f with respect to y is 0 plus y, so y. and derivative of f with respect to z is x, which also works. So it looks like my guess was correct. So I sort of think of this guess and check method as being pretty effective for answering questions like this, rather than trying to do something that's maybe more precise, but a lot of work to keep track of. I'll also remind you that a lot of vector fields don't have potential functions. We've seen that some do and some don't, but it's not hard to come up with ones that don't. For example, 0x squared has no potential function. And the way you can check this is that the curl, in this case the 2D curl of f, is, well, 2D curl of f is supposed to be qx minus py. In this case, this ends up being 2x. But if f is conservative, that is, if it has a potential function, the curl should be 0. And so this tells you it's not conservative. It has no potential function. Again, the factoid to remember here is that curl not equal to 0 means that it's not conservative. The next bit here was about line integrals, and we've had some practice actually calculating these, and you should be able to geometrically identify when a certain line integral is positive or negative or 0. But what I'd like to focus on right now is the part about the fundamental theorem of line integrals. And let me just remind you what it says, what the statement is. The statement looks something like this. That I'm just going to write it down, and then we'll try and interpret it. That it's f of the end minus f of the starting point. Okay, so what I'm sort of imagining here is when you have a line integral, you have a vector field in the background and a curve c that goes from one point to the next. And so if I start at point A and I end at point B, then I'm doing f of b minus f of a. Now the question here says, under what circumstances does it give you a shortcut and when does it not? So for some line integrals, this seems like a really easy way of calculating it. But there's a situation in which it doesn't apply. Not every line integral can be simplified using fundamental theorem of line integrals. In particular, this gradient of f is important. If I asked you to find the line integral of 0x squared along some curve c, well, we saw that this is not conservative. This is not the gradient of any function, so fundamental theorem of line integrals doesn't apply. The vector field is not conservative. Now, the thing to notice about the fundamental theorem of line integrals is that I can calculate if the vector field is conservative, if the vector field is the gradient of some underlying multivariable function, I can calculate the line integral without actually doing anything with the path c. I just need to know the start point, the end point, and the function. And so that sort of tells me that the path I took from A to B doesn't matter. And so this is what leads to what I sort of think of as the conservative vector field theorem, although you might not have called it that in your section, which says the following. Oops, hold on. It says that a vector field f is path independent. That is, the path you take from A to B for a line integral doesn't matter if and only if f is conservative. That is, if and only if it has a potential function. Now look, I just went through a lot of material very quickly, and if you weren't following along with that, that's fine, but you should go back and watch the videos, go back to the worksheet and try and remember how all these pieces fit together for line integrals, what it means to be conservative, what it means to be path independent, what a potential function is, what the fundamental theorem of line integrals says, etc. but this was supposed to be a reminder of some of those key points, some of the points to go back and study. Okay, the next topic is kind of a big one, and it's an important one, which is parameterizing surfaces. So I'm going to go through the three examples that are listed here, and just as a way to sort of illustrate some of the techniques that we want you to be familiar with. So here is one of the examples, and the technique that I like to use is to start by choosing a coordinate system. Here, it doesn't seem to be helpful to change into polar or spherical or cylindrical or anything like that, so I'm just going to stick with Cartesian here. And then the next step is to pick two of the three coordinate variables as your parameters. And then solve for the third one. So you want to be strategic here. In this case, I'm going to say u equals x and v equals z. The reason why I'm not making v equal y is that y is already solved for. So if I make my parameterization, and remember, your parameterization, you're always trying to tell me what x, y, and z each equal. So I should tell you x, I should tell you y, and I should tell you z. You want to make these blanks as easy as possible to fill in. So u equals x, all right, x is u, v is z, so z is v. And then I can write down y in terms of those two things. It's x cubed, so u cubed, plus sine of z, so sine of v. I also want to include my parameter domain. I should say what values of u and v I should include. Usually the way to do this is we'll ask you to draw in the UV plane what values to use, and then as a next step in certain problems you might need to set up inequalities so that you know what to use as your limits of integration. In this case we say x goes from 0 to 2, so u being x goes from 0 to 2, v goes from 0 to 3 since that's z, and so I can say that my parameter domain is just this region where both of those things are true. Here in the next example, this seems like a good candidate to use for cylindrical coordinates because I have an x squared plus y squared here. So I need to decide among the three cylindrical coordinates, r, z, and theta, which ones to use as my parameters, u and v. Now let me first start by rewriting the equation. It'll be r squared equals z cubed plus z. So I need to pick two of the coordinates as parameters and then solve for the third. So among r, z, and theta, which one seems to be the easiest to solve for in this equation is a question you should ask yourself. It seems like theta's not in the equation, so I shouldn't try and solve for that. Z would be kind of tricky to solve for because there's a z cubed and a z here, but r I could solve for. And I could say that r is equal to plus or minus square root of z cubed plus z, but I actually don't need the plus or minus because z is positive, so z cubed plus z will also be positive. So I can actually even just do without that. So this actually helps us out in deciding. I can solve for r easily, so let me use the other two variables, u equals z and v equals theta, as my parameters. And I could write down r of u v. Okay, again, I need to tell you my x, my y, and my z here. Well, let's see. I know what my z is. Z is just equal to u. And the x and y come from the coordinate change equations that we know. X is equal to r cosine theta. Y is equal to r sine theta. So let me just write r and theta in terms of our parameterization that we have in terms of u and v. So r is really going to be, well, let's see, square root of u cubed plus u times cosine of theta, which is v. Again, r is square root of z cubed plus z, so u cubed plus u, times sine of theta, which is sine of v. And then my parameter domain, again, comes from the inequalities. And this is maybe a good sort of third thing to write here. Parameter domain comes from your inequalities. So I can say exactly what the values for z are. Z seems to go from 0 to 3, so that means that u is going to go from 0 to 3. And v being theta, well, there's no restrictions, so I should say that v goes from just 0 to 2 pi to go over the region just once. And for most of the applications we use for this are things like surface area and flux, things where you don't want to be double counting, so I don't want to just let theta be negative infinity to infinity or something like that. I'll leave the last example for you in spherical coordinates, but it's a similar technique would apply for coming up with the parameterization and parameter domain for that one. The next point is about surface area, and with regards to this last question, I'll remind you of something I didn't mention back when we were talking about cross products, but another way of interpreting the magnitude of the cross product is that this is the area of a parallelogram spanned by RU and RV. And while it might not be super clear what parallelogram I'm really talking about here, if you remember when we've drawn these pictures of parameterized surfaces before, it sort of draws a grid on the surface. You've probably seen a picture of the parabola with the parameterization sort of drawn on it as well. And the parameterization ends up dividing the paraboloid into these parallelogram shaped regions. And so this formula shows up, this magnitude of the cross product shows up because it's basically figuring out the area of each one of those little parallelograms after you've sliced it up in the way that integrals always slice things up, and then trying to do the thing you were doing overall, in this case finding area, just one slice at a time. So finding the area of one slice of these things at a time. So the next point is about flux. We do want you to be able to describe geometrically what's going on, but let me take a second to talk about orientation. When we say orientation, we're sort of describing which direction of flow through the vector field should count as positive, and then the opposite direction counts as backflow, as negative. And the place where you need to be careful when you're actually calculating one of these things is that at some point in the calculation, you're going to use something like RU cross RV, or you're going to come up with the unit normal vector n, and you have to decide, you have to make a conscious decision to decide if the equation you came up with here, the equation for the unit normal vector or the RU cross RV, is pointing in the positive direction or not. And if it doesn't, that's okay. If it's pointing in the opposite direction, it just means you need to slap a negative sign in front of your entire integral. It is something that you should check, and usually you'll see a descriptor, something like the upward flux or the outward flux or something like that. And you'll need to check your formula for RU cross RV to see if, well, if it says upward, if the z component is positive. If it says outward, you'll need a way of checking that. And so that's something that you do need to do in each one of these problems so that you're not off by a negative sign in the end. Along with these last couple of points, let me remind you that there's really two equations that come up for flux, two formulas that you have. The notation we use for flux is this. So this isn't really a formula, it's just sort of telling you the thing we're trying to find. But there's two ways that we write this down. The first way we write it down is that we say, okay, this should be f dotted with the unit normal vector, and then times this thing that we call RU cross RV, the magnitude of du dv. And I'll do this over the parameter domain D. Now, the thing I want to point out about this is that this whole bit right here, this is the thing you integrate to get surface area. Sometimes it's written as ds. So remember that the double integral of over the parameter domain of just that part, this is equal to surface area. So that's one formula. If you know the unit normal vector, then this is sort of a quick formula to use. If you know what n hat is, then this might be a shortcut. You might not need to do as much work if you read it that way. The other formula that is useful is to write something like f dot ru cross rv du dv without any magnitude signs. This is the other formula that's useful here. In general, this is probably the one you use in a lot of the problems, because in order to calculate this ds, you need ru cross rv anyway. So it's not really, seems like it wouldn't be much more work to do it this way. In fact, it seems like you'd be saving some work doing it this way. And that's fine, that's true. But for a question like, number 4 down here, it's actually useful to know that first formula. If I know that f dot n is 3, it's constant, and the surface area of u is 7, let's try using the first formula I had to answer that question. So in that situation, I'd be saying, okay, f dot n times ru cross rv du dv. Well, this f dot n is just equal to 3, so I can pull that 3 out. But then this bit right here is just the surface area. And so this ends up just being 3 times 7, or 21. This f dot n is sometimes called flux density. You can think of it as the amount of flow through per unit area. So if that's constant, you can just multiply the flow through per unit area times the area to get the total flow through, to get the total flux. If you've at a point in the class watching this right now where you saw the first lesson on flux but haven't done the lessons on Stokes' theorem and divergence theorem, this might be seeming a little bit weird to you. This might be something you haven't seen before. But once you get to those later classes and see the examples using Stokes' theorem and divergence theorem, you'll see this second, or rather this, I guess the first one that I wrote down here using the f dot n a few times, and you'll be able to answer questions using this sort of shortcut formula once you see that. The last unit is on what we're calling vector analysis, which has to do with divergence, curl, and then the 3 integral theorems that come at the end that have to do with these things. First of all, I'll mention that these questions about divergence and curl and 2D curl, there are formulas for these that you can look up, but you should also be able to characterize them geometrically. And in fact, you can probably imagine those would make pretty good multiple choice questions. For the 3 theorems, Green's theorems, Stokes' theorem, and divergence theorem, I do want to point out that there are the same few things that you need to be careful of for each of them. If you're trying to write down what Green's theorem says, you should make sure you know the equation for Green's theorem. You should be able to know the relationship between the different variables and expressions inside of your equation. You should know what each one of those variables means. You should understand the role that orientation plays. And you should be able to draw a picture of what's going on. So that applies to Green's theorem, it applies to Stokes' theorem, and it applies to divergence theorem. So I'll say a little bit about Green's theorem in particular. I'll draw a picture, state the theorem and stuff. I'll do that for each of these theorems. But I do want to point out they do all have kind of this similar structure that is kind of useful to remember, that they really all have the same elements and kind of same things that you need to be careful of as you're calculating things with the theorems. So Green's theorem, and I'll just kind of make some room here, only applies in R2. And the situation is that we have a region R in the plane that is surrounded by a curve C. So there's two pieces here. There's the curve C and there's the region R, of which C is the boundary. And the theorem says that if this is true and we have a vector field in the background, I'm not going to draw the vector field, but there is some vector field here. It says that the line integral along C should be equal to the double integral of the 2D curl. So here f is equal to PQ. Now there's one thing I haven't told you here, and this thing is quite important. I didn't tell you how to orient C, and the way we usually say this is if you walk along C, you should be keeping R to your left. So in this case, to keep R to my left, I should sort of be going counterclockwise around R. As you can see where orientation comes into play. There's an equation here that you need to know. And you also sort of need to have the picture in mind in order to know when Green's theorem can be applied and how it can be applied. And the equation sort of lets you know what sorts of applications are feasible here. One kind of thing you could do is if you have a line integral that seems tricky, you might be able to turn it into an easier double integral. You have to be careful though, because in order for Green's theorem to apply, you need a curve. The curve C has to surround a region, has to be the boundary of a region R. If it's not, Green's theorem wouldn't apply. Green's theorem only applies when the curve C is the boundary of the region R. But you might be able to use it to turn a difficult line integral into an easier double integral. And then another application that I'll refer you back to the notes for is using Green's theorem to find area, because you can set up area as the double integral of the number 1 and then turn that back into a line integral. And again, I'll refer you back to examples we've done about that. Next comes Stokes' theorem, which you can think of as a certain 3D analog of Green's theorem. Really, Stokes' theorem and divergence theorem can both be thought of as analogs of Green's theorem in higher dimensions. So for Stokes' theorem, since it happens in R3, I'm going to start with a surface R whose boundary curve is C. So I'll call the boundary curve, in this case the boundary curve really has 3 curved parts, and then we have a 2D surface living in R3. And again, there's an equation associated with the theorem. It says that if you take the line integral, it should be equal to, well, not quite a double integral, and R is maybe not the best letter to use here. I should really be using something more like S or U or something for surface, but I'll still call it R anyway, of not the flux, but the flux of the curl of F. Okay. And so again, I'm sort of missing the same element here for orientation. There's actually 2 things I need to orient. I need my surface to be oriented in order for flux to make sense, and I need my curve to be oriented so that the line integral makes sense. And so I need those 2 to be compatible. So let's say that R is oriented so that the normal vector and hat is pointed upwards. We want the upward flux. So again, I want to be able to walk along C so that I'm keeping the surface on my left. And this is if I'm keeping my head in the direction of the unit normal vector. So I'm imagining a little person right here, head in the direction of the unit normal vector, walking along the curve C. And so which way would they need to go to keep the surface on their left, the same way we did in Green's theorem? And you have to visualize this a little bit, but it seems like they need to be going, from our view, I guess kind of counterclockwise, going this way. But depending on which way n is pointing and which way we're viewing this, it may or may not be counterclockwise, and also depending on your viewpoint. So just saying counterclockwise is not really enough here. If n had pointed the other way, the person would have to walk the other direction around C. We need the two orientations to be compatible, and again, that's a matter of when the person walks along the curve with their head in the direction of the unit normal vector, they should be keeping the surface to their left. So the kinds of applications we can do here are, well, we can turn a line integral into a flux integral. So maybe for some reason the flux integral is easier than the line integral. Or we can turn a flux integral into a line integral, but I do want you to be careful here because you can't do this for just any flux integral. This is a flux of curl integral. And I'm taking the flux of the curl of f. If I was just taking the flux of f, the Stokes theorem wouldn't apply. But if I do have a flux of curl integral, I could convert it back into a line integral, which maybe would be easier. The last theorem is divergence theorem, which also applies in 3 dimensions, but in a little bit different situation. So I'll keep my 3 axes. This time, I have a solid region that is bounded by some kind of surface. So imagine that I have the surface of the cube and then I'll say that C, or usually we use a letter like E, is the solid inside. Okay, so I have a solid region and then the surface of that solid region. And what divergence theorem says is that if I take the flux of a vector field through the surface U, that should be equal to the triple integral of the divergence of the vector field f. So again, I need to say something about orientation here, but this one is a little bit easier to state, that I always want the orientation to be outward facing. So the outward flux is equal to the triple integral of the divergence. Yeah. So the kinds of examples you can imagine, I can either turn a hard flux integral into an easier triple integral, and then you can actually turn some triple integrals back into a flux integral, but the more common thing is that since flux is usually harder, we can turn flux into a triple integral, which might be easier. Again, I'll sort of say there are limitations here. This doesn't apply to just any flux integral. You need the surface U to be the boundary of a solid, otherwise you can't make this conversion. The final thing that I'll say here is that there are a few concepts that have shown up several times throughout the semester, and it's a good exercise to go through to reorganize these things in your mind. For example, something like line integrals has come up in different units at different times in different contexts, but on the final exam there might just be a question that's like, calculate this line integral, and you'll need to be prepared to decide which of the things you know about line integrals will be relevant for calculating that line integrals. So in order to get ready for that, it makes sense to kind of go back and look for all of the places in all the classes where we learned something about line integrals and make a list. And then that way when you see a line integral, you'll sort of have in your head, okay, these are the different options available to me. Is it line integral using Green's theorem? Is it line integral using Stokes' theorem? Is it line integral using fundamental theorem of line integrals? Is it something I have to calculate directly? There are lots of different possibilities, and so kind of having that list in your head will be helpful. The same thing applies to a lot of other concepts that have showed up at various times You've learned a lot about gradient. You've learned a lot about tangent planes. You've learned line integrals, flux integrals. We've seen a lot of different equations for surfaces, and it might be good to sort of like go back through a bunch of examples of that. Same thing with parametrizing surfaces and parametrizing curves as well. And then the last thing I'll mention is using contour plots. I know has been a challenge throughout the semester, but kind of going back and remembering all the different things you can do with contour plots, things that we've asked you to do in terms of gathering information about the function by looking at a contour plot. Okay, that's the end of my little summary here. I hope it was helpful, and definitely go back and review the things that you feel like you need to review. I didn't cover all the bullet points here, so make sure to kind of go through some of the details that maybe I didn't talk about that you might still have questions about, and feel free to bring those things to office hours, etc.